Thanks to organizers for this opportunity to talk about emulators. And I'm really sorry that I couldn't make it to the in-person meeting. And as some of you know, like in the audience, that I have been worked a little bit on the heavy ion phenomenologies some time ago, in particular related to the initial state. But now I'm really focusing on the low energy nuclear physics. I never expected, but now it becomes true that yeah, these two things actually can be connected, and hopefully we have a very nice discussions through this program. So Christian already mentioned emulators. In fact, in the previous talks, emulators come up quite frequently, and associated with that is the Bayesian statistics also being mentioned, and they are also somewhat connected. My plan for the talk is, let's see, can I move it? This plan, like I will discuss emulators in general terms. So roughly speaking, there are two main types of emulators: projection-based ones and then data-driven ones. And so as far as I am aware, like the data-driven emulators have been used in heavy ion collision physics. But as Christian also mentioned before, it clearly has been used in nuclear matter equation state. But then I will discuss the projection-based emulators, in particular in the low-energy nuclear physics, and I will tell you some ongoing collaborations, demonstrations in the hadronic physics as well. In the final part of the talk, I was just trying to pose the question whether the emulators, in particular for nuclear structure, could be relevant to the topic of this program. Now, so just I feel like this is really not needed anymore, the definition of emulators, but just want to come back to the basic understanding of the concept. To me, it's really enables interpolations and extrapolation of your physical models in the parameter space, right? The starting point is always you have a parameterized physical models, and then you want to explore the parameter space, and emulators is provide a way for you to very fast to interpolate and extrapolate the model output in the parameter space. And it's useful, first of all, for model calibrations, because when the model is expensive to solve, just repeatedly, like for a million times in the like high dimension parameter space, is not feasible. The other important application is actually taking advantage of its good extrapolation, taking advantage of extrapolation capabilities. So you can always set up your parameter space, set up the parameter space in a way that part of the parameter space that correspond to easy calculations, the other part or in the other region that normally actually we want to solve actually correspond to hard problems. So the one approach is to use emulators to extrapolate your easy calculations to the hard region. But of course, this really requires that the emulators has very good extrapolating capabilities. So unfortunately, I will not go into these second applications. For the purpose of this workshop, I will focus on mostly on model calibrations. So as I mentioned, there's two main types where we start with projection-based. The terminology Christian already mentioned at the beginning. One particular method, the important method is called the reduced basis method. And actually, the funny thing is in the nuclear physics, we started paying attention to this type of ideas really from this paper, 2018, I believe led by Dean Lee's group. And it was called eigenvector continuations. And as later in this, as explained in these three papers and possibly others, that it turns out there is a field called the model order reduction that have been being pursued for quite a while, and there's different approaches. The so-called reducible method really come from that field, and it's very similar to the EC idea. So the emulators is very intrusive, meaning that when you develop these emulators, you actually need to understand the equation systems of your physical models. So simply speaking, that means that you have to build new code for emulations. But based on our experience, it turns out it's actually not that bad. The emulator, because the emulation structure is actually quite easy, quite simple. And then exactly because of that, that means the emulator itself has already a lot of physics built in. So that in general tend to require less training data and also more robust extrapolation capability as compared to the next one, the data-driven ones. So data-driven ones, there could be like Gaussian process that have been come up a lot, and a big chunk of application of neural networks is also essentially about emulations and extrapolation, basically interpolation, extrapolation, some unknown functions. Okay, and it's non-intrusive because it just looks at your data, right? Your model output and how it depends on the input parameters, so data points. It doesn't really look into what the underlying physics equations. But unfortunately, because of that, it does require a large amount of training data. And as my experience informed me that they tend to have worse extrapolation capabilities. So the emulators, in particular Gaussian process, have been mentioned several times in the workshop. It really has been used significantly, like extensively in the heavy-ion collision physics. I think a lot of these two papers is the basically is trying to apply, want to extract the QCD, the QGP matter properties out of heavy-ion collision data, but they want to do it in a Bayesian statistic framework. And as you know, that means that you need to sample a very large amount of model calculations in the input parameter space. And it turns out the heavy-ion collision simulation itself is a very complicated, intensive, computationally intensive calculations. It's required. It has multiple stages, and so this is the initial state, and after some process that we don't have a consensus on, the system actually equilibrate. The system that people applied the hydrodynamic equation to describe the system, and it spatially expand, and the system cools, then the dynamic degrees of freedom become hadrons, and then they keep expanding, and then eventually the hadron cease to interact, and then fly to your detectors. Okay, so it's multiple stage simulations. So they, as I said, then emulators is a critical component. Even though it's a component, but you can imagine, right? If without it, basically you cannot do anything with Bayesian statistics in this area. Now, the second paper is actually about jets. So in the collisions, you could have very energetic parton-parton collisions, and they produce jets, and these partons will transverse your medium, and because of the color interactions, and will significantly lose interactions. The people's hope is to use them as a probe to also understand the properties of the QGP. So this is the Q hat is another parameter of interest. And then, as you can imagine, besides modeling the medium evolutions, on the top of it, you have to track how these partons moves in the medium. So it's quite challenging modelings, and emulator is very important. I feel like yeah, I may just spend a little bit of time on what the Gaussian process really does, just in case that some of you still haven't really really get used to this concept. So imagine, right, you have one parameter, x, and y is your output, some important observables like multiplicities or particles at particular momenta. So the y is a function of the x, right? So in principle, your model or the theory will provide this relationship, but without actually evaluating those models, you don't know the curve, you don't know the relation, you don't know exact dependence. Now, so the Gaussian process using that as emulator is really thinking about the simulation as a data. Okay, not experimental data, but the data from simulations. So before you do that kind of experiment or simulations, you have some prior knowledge about what this function could look like. So imagine you have some space the space for these general functions. Okay, so the Gaussian process basically gives you a very fast way to sample those functions. Now, the inside of the machinery, there's so-called not hydro, the hyperparameters. Okay, it's related to how the points here and points on the other location are correlated. So before you have data, you have some prior knowledge. This means you have some, you believe that the function should be somewhere in that parameter space, localized. Okay, then as soon as you run the simulations for a few times, you have more information. The input data, and then based on Bayesian theorem, you can add the information on top of your priors, and suddenly the localized the region or the variance for these possible functions get reduced. Okay, so then the location of credible functions in that space get reduced. So then you have this more tighter the bands here. Okay, so then you have a mean and you have variance. As you can imagine, you put more and more points, eventually you have a better, smaller and smaller uncertainties coming out of this process. So 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 this is basically what people mean by Gaussian process-based emulators. Now, there's also neural networks, so it doesn't give you some kind of some uncertainties or variance, but basically say that it can approximate any functions with very good accuracies. Again, it has hyperparameters inside the inside neural networks. So and then with your simulation data becoming available, you condition those functions to those data, right? And suddenly you can calibrate your hyperparameters. Then these functions can be used to interpolate and extrapolate the points that you collected from simulations. So this is a one use application of neural network for emulators. Now, the important thing here is that these different approaches can offer a very fast way to evaluate these functions without running the models. Okay, and so now now I'm going to explain the projection-based, in particular reducer basis method-based emulators. This is a very different approach. So imagine now you have a solution vector from some equation system with models. Okay, I call it psi, and it lives usually in a very high dimension space. Okay, what I mean by that solution vector. So imagine you want to describe the dynamics of object, the mechanics of object, like the surface of this object. You digitize it, and then you collect the space coordinate of the points and put in a vector. That basically is your solution vector. So the dynamics of the system will become how the vector moves in this space, right? You can imagine that you can easily get a very large number of points on this on these objects, and then this dimension could easily explode. Now, so imagine now you have two parameters for this particular system, and now if you fix theta2 and you move theta1, okay, so then the vector will move too in the space, but it will actually map out a one dimension curve in that high dimension space because you only have 1 degree of freedom here. Now, if you go a little bit further away from this line, you go to another line, you actually map out another line, right? So by continuity, you actually, in this patch of the parameter space, you literally map out a manifold, but the manifold is 2 dimension. So the key point is if you have 2 degrees freedom, this manifold is 2 dimensional. So then this is much smaller, right? Much smaller than usually high dimension, these high dimensions, because this dimension can be millions or billions in nuclear problems. So then the problem becomes, okay, is there a good way to find out a good basis to expand this manifold, okay, to expand these vectors? And so the reduced basis method basically says you just, you sample the parameters in the parameter space, collect your training points, and use those solution vectors as a basis. So suddenly that you have a basis that is very adaptive to your problem because they come from solution of your parameterized problem, right? And so the important thing is that you just need a very small number of bases. And so then the problem becomes, if you want to get this precise solution at the other points, then the problem becomes finding the weights in front of these bases, right? So if you have 3 training points, then you are dealing with 3 unknowns for different theta values, okay? And to do that, to find out weight, there's different approach. There's a variational approach or the logarithm projection in general. You basically plug these ansatz back into equation system and finding out smart ways to get these coefficients. Okay, but the important point now is you're dealing with a low dimension calculations, sometimes even just a low dimension linear algebra problem. And because the assumption here is that the manifold actually curve in a very gentle way, so this means your calculation need to actually be able to be sensitive to small changes. This means the solutions of this vector need to be precise enough. Now, based on this picture, then you can see, well, it actually fails, right? So imagine just 1 degree of freedom, 1 parameters, if this tip like moves crazily in this whole like very high dimension space, then it's going to be very hard for this method to work. So now I'm going to talk about how people use that, using it in the low energy nuclear structure. Nuclear physics. First is nuclear structure. So the nuclear structure, simply put, is trying to solve eigensystems of a parameterized Hamiltonians, but its dimension grows exponentially with number of, say, nucleons in the nucleus. Okay. The basic equation is this, as I just said, it's finding the eigenvalue. Suppose the lowest energy would be the ground state energy or binding energy. The phi would give you the nuclear many-body wave functions. For the emulators, it has 2 stages: the offline, online, and you can, as I just alluded before, this is more like a training stage. Online is more like an emulation stage. Okay. The idea, as I mentioned, is first you sample some points in your parameter space, and then the ansatz is a linear combination of your solution vector give you ansatz for your solution vector in all the other points. So the problem becomes finding 3 weights for different theta. Okay, so effectively this means your Hamiltonian matrix get projected to a very low dimension, 3 by 3 matrix, and then the emulation becomes, the beta here should be C here, the emulation becomes solving this little eigenvalue problem. So it's much quicker at emulation stage. This is a toy model demo. To imagine that you have 1 particle, you have some interactions. So we're doing quantum mechanics, trying to find the ground state of the system. Yes, imagine you have 3 parameters. Okay, theta 1, theta 2, theta 3. In that 3-dimensional space, we use just 6 training points. Okay, I want to let us think a little bit. 3-dimensional space, 6 training points. That's incredibly low. The training wave functions, okay, so like the gray lines, and then there's 3 different validation points, I believe. And the curves, the black curve is exact solution. The dots are the emulation results coming from this reduced basis method. And there's some other generic, actually harmonic oscillator bases. You can see that these bases are really not adapted to the problem. Okay, it has a lot of features that this solution actually doesn't have. So then you can look at, say, ground state energy. These are actually residuals, basically means the emulation error. And you can see like consistently reduced basis method is much better than this generic basis. And of course, based on 6 training points, we have input thetas, and then we have output energies. So we can use apply Gaussian process emulators and train them. This would be the emulation error. Okay, and related to the topic of this program, we can also think about the radius, which is one particular characteristic thing, property of your spatial state, spatial distribution of your wave functions. This is radius, and this is like the projection-based emitters do way better than Gaussian process based on just 6 training points for 3-dimensional space. So people really use this in the realistic structure calculations. So this is a helium-4 and 3-dimensional input parameter space, 12 training points. You have 3 different type emulators, in particular the EC or IBM based emulator that really beat the Gaussian process. So then people apply the same idea to a different calculation framework for a larger systems. Again, similar story here. So the punchline of the paper actually is that 16-dimension parameter space, they did sample like 1 million calculations, 20-year calculations get down to 1 hour on the laptop by using these type of emulators. And the other thing I want you to take away is actually you see the training points are here if they do that. And then the emulator actually can extrapolate to a different region. You feel like there's a region here. The emulator already can capture this turning over based on these training solutions. And I believe also the Christian mentioned that, and I believe this will come up later in the program. The people apply this method to emulate the density functional solutions. Okay, I think this might be very valuable to have the ion now, in particular the nuclear structure aspect. So we are so then about continuum physics or it's the same Schrodinger equations, but now it's not solving the eigenvalue problem, but say for a particular beam energy, you're trying to solve these differential equations, okay, with the different boundary conditions. And this is it's a harder problem, even for few body systems, it's already like computationally expensive. We apply this RBM idea to demonstrate the RBM emulators for 2-body scattering, and later we generalize it to 3-body, and then you really see that for generic 3-body simple problems, the time scale for emulation at one particular parameter millisecond, and then on the laptop, and the emulation error can be extremely small. Okay, the typical realistic 3-nucleon scattering actually normally performed on big clusters for I think on the order of 1,000 seconds for hours. So and that was for the few body continuum physics, and then I think it's also relevant for hadronic reactions. So I'm collaborating with one of the experts in the field. For example, we were exploring its application in electron-positron collider physics for the heavy quark systems. Again, you have different models, but eventually, like using either quark degree freedom or hadron degree freedom, but eventually the model is centered around some sort of equation system. And the idea is to apply the RBM general principle to see the seek emulation for those equation systems. So here, you imagine you vary one particular parameter in this vertex, right? And there's a component that relates to this differential cross sections for these 3-body final states, this FP component. So these very preliminary results for one particular parameters, 1-dimension parameter space, almost 3 parameters, three training points, you can get a very good emulations out of it. Now, I also want to say that it's also going to be, could be relevant for lattice results. So for example, in this paper, they basically apply this type of emulators to calibrate this Pauli EFT field theory. Basically, it's a theory describing nuclear interactions for the few nucleon system in lattice setup. So the lattice QSD are different from the equation of state calculation in the heavy ion physics. The few body, few hadron calculation using lattice method is really about solving few hadrons in a periodic boundary box. Okay, so they cannot directly solve the problem in the infinite volume, but they can always solve system in a large box. So the idea now is then to calibrate these kind of models or theories to those energy levels. Okay, to can solve the eigenstates, energy levels, output, and then the hope is to calibrate the underlying the parameters, and then let the models to make predictions in other places, in the nucleus or in the infinite volume. So it's so I see like it's going to be quite relevant for this area too. Now, just how much time do I have?
So you have 5 minutes until your 10-minute discussion.
Okay, yes, that's good. About the relevance for this program, And when I started working on this type of emulator, projection-based emulators in particular, I always have these questions: is so what about possible projection-based emulator for relative hydrodynamics calculations? After all, it's a equation system, and actually the model reduction, a big chunk of the model reduction research is about hydrodynamic calculations. Okay, that would be interesting to know. The real question for me is actually whether there's a relevance for this projection-based emulator for nuclear wave function for connecting the nuclear structure to heavy ion simulations, right? But I really enjoyed the talks this morning, right? The Lewis talks, like worrying about the model dependence, because literally before his talk, I write these sentences and these points having the same doubts is, can we actually define those inputs that you need in terms of matrix element of orbiters so that we can be away from skin scale model dependence? So I think right now the practice are centered around DFT, centered around the one body densities in the intrinsic frame. But that's really a definition in a particular theoretical framework, okay? And and as we know, learned in the nuclear structure is that actually the wave functions, you can always make unitary transformations on the wave functions, okay? And then the same time, if you make the same related transformation on your operators, your matrix element, your physics won't change. But imagine now if you define everything in terms of wave functions, then when you apply transformations, you suddenly lose control. You don't know which result should be better. So that's what I mean. And the other thing is that people are comfortable right now with this thinking about you have a deformed rotating liquid drop. It is deformed in the intrinsic frame, and actually some of the like rotate isotropically, the frame rotating isotropically in the free space in your left frame, right? But the question is actually, do this approach actually can explain systematically all the multiple particle correlations? That's clear. That's not clear to me that it actually does, because yeah, actually the reason I am interested in the topic of this program is actually multi-nucleon correlations. Based on my own limited knowledge, like nuclear structure physics haven't really worked on multiple particle correlations a lot. The most observables are based on the electromagnetic probe or electric probe, and that probe normally means you're really probing a nucleon at one time, okay? And there's rarely the case that you actually, the processes that people have studied involve multiple nucleons. Two nucleons, yes, like even neutrino suburban decay, that process involves two nucleons at one time. But many nucleons at one time, I don't see that. So I think the heavy ion collision is a real opportunity, but at the same time, that led me to think or ask this question, whether those multiple particle correlation can be, like from a basic principle, can be casted in terms of a shape in a reliable way. And just to bring this up, this is about fish behaving collectively in the water. And you see, like, yes, you can see clearly there's emergent geometry out of it. The large distance correlations can be described using geometries, but it's very hard to convince me that all the multiple correlations can be cast using geometries. Now, just summarize, emulators are critical for fitting complex models. That's the main message. The two types of emulators are being used in nuclear physics, but somewhat like one particular method in one area. But it's better to see actually crossing. And I have to say that actually the data-driven ones also being used in the large nuclear physics, equational state, and all the others. And I sense that nuclear structure emulator could be relevant, in particular if you want to assign, again, assign uncertainties or propagate uncertainty from your input nuclear structure, the input for nuclear structure calculations, like underlying nuclear interaction, all the way to multiple correlations in the initial state for the heavy ion collisions. If you want to do that, I think emulators could be very useful there. And the last point, a very generic point to advocate for emulators, adoption of emulators, because I think just in a very general way to say it is that people have invested a lot in the large calculations, expensive calculations, right? But for the other users who want to use it, it's very hard because you cannot run it. It takes a lot of resources. So if you actually have emulators in future for the large calculations, all the others can access those calculations through the emulators. So that will really help building connections between different research areas in general. That's all. I'm open to your questions.
Very much, Stephen. Go ahead, Yang.
Thanks for the talk. So I have a question. So actually two parts. The first one is, your emulator can handle nonlinear issue. Like, if this is linear, to me it's quite simple, but if the evolution is very high, there's lots of nonlinear effect. Can you handle this? Second part of this question is like, what's the difference between emulator and machine learning? I can train my machine, I can do the things in sort of like black box. Then I can actually also do some prediction. So what's the difference between these two methods in terms of pros and cons?
Yes. So the answer to first questions, this is actually the point of this slide, right? So if this solution manifold, it actually boils down also to the how large of space that you want to explore. So for a given patch of experimental space, if the solution manifold looks like that, gentle, not twisted crazily, then this type of reduced method can handle. But and it's really about dimensionality. If this intrinsic one-dimension curve, by when you explore this parameter space, it moves so much that effectively covers the whole dimension of the full space, like a million dimensions, then there's no hope for using this method. But for more gentle problems that we encounter in the nuclear structure, like for example, this type of method works. Okay, so like people see the ground states behave, the vectors move in the low dimension manifold. And for the second question is actually this slide, right? So the data-driven ones, as you said, like the Gaussian process people have used. The neural networks do similar things, like it has some, right? The claim is that it can parameterize, can approximate all the functions, continuous functions, and it has its own hyperparameters. So if you calibrate those parameters against the training data, of course, you can do interpolation and extrapolations. So, but the point of this slide here is actually the reason that it's appealing to a lot of people like us in nuclear structure for the reduced basis method, because it has a much better accuracy. And I didn't mention it has in general better extrapolation capabilities. Because it actually built a lot of physics into emulations. The data-driven ones, they just look at the data to learn from your data. So in principle, it really requires a lot of information to really pin down well the true functions in that function space.
Yeah, so I have two fairly disjoint questions. The first one is kind of going back to Jin Young's questions. Imagine you have a relatively smooth parameter space, but at a certain regime, then things become crazy. Is there a way to build this into your model, especially if you kind of know or anticipate where that regime is? And then my second question is at the very end, when you're talking about how to put a nuclear structure in a better way to connect that to heavy ion collisions, one thing that, I mean, would actually be ideal for us is if you just give us nucleonic configurations. So are there ways that you can think about better sampling methods to include like these multi-particle interactions? Because it would be great if we just get the nucleonic configurations and use that directly.
Let me jump to your second questions. Actually, this actually comes back to one question raised in Christian's talk. Is about ab initio calculations for the nuclear structure for heavy elements, right? So how reliably can we actually trust ab initio calculation? So that's a basic a starting point, and then we can start thinking about whether it can be applied, should be applied in initial state. The point, like I mentioned, like a multiple particle correlations haven't, based on my knowledge, haven't been really checked using data, is because because there were no really many data like you really touch on multiple nucleons at once. Okay, the ab initio methods, in particular going to larger nucleus region, they are like there's a lot of approximation going to that, and most of the energy driven, like the trying to get a good wave function to lower the ground state energy, for example. But if the multiple correlations in particular, it's not sensitive or doesn't contribute much to the energy, but very important to your data, to your heavy ion collision simulations, then the question is whether we are really can trust those ab initio calculation, multiple particle correlation. So put another way is that actually, if you can go backward, heavy ion data will actually give a very good input for nuclear structure, in particular on the multiple particle correlation front. But that requires you to have some model independent way to define some key quantities that so both sides can talk based on that. And right now, and that quantity is actually tied to the dynamics, right? How the nucleon collides, and how the nucleon collides. So basically, right now, picture is in the collisions, you are projecting out the space coordinate of nucleons in the wave functions. But actually, there's a lot of dynamics into that. There's operators responsible for that happening, and that I think that may be the source of the answer for here, is trying to have a way to understand what's going on there, and then we can write down relevant operators. So yeah.
Okay, next question to Bill.
A naive question from my part, but some cases you're working, for example, you want to emulate something that comes from field theory, and you ever have to worry about singularities when you construct your emulator, so that you don't, I mean, there are holes in there for propagators and stuff like, do you ever worry about singularities?
Yes, right. So if you like, when I say singularity, if you have a singularity in the parameter space, like have a poles here, and like solutions actually become changed crazily in that at the pole, right? So then the extrapolation, that's actually essentially about extrapolation. So the extrapolation error will blows up at the pole, right? So yes, singularity definitely matters. And this actually comes back to the previous question. The first one is about whether you can detect, like self-detect the region that the reduced spaces method won't work. What I can tell you is the approach people do here is trying to say, do as much as you can do, right? To sample parameters, points in the parameter space. And what they do is like to look at the solution vectors and put them together, do SVD, singular value decomposition to data matrix, and to see whether the singular values or the relevance of different solution vector have this good like the structure, like that going down, the singular value will going down when adding more terms. If the singular value stay like a flat for when you keep adding more vectors, that actually means that this method doesn't work if you as you construct it. But there's ways. So this is actually an active research area. This is not like the end of the story. So there's different methods trying to attack this problem. And in particular, I didn't mention here, there's overlap here. So people trying to combine these two different methods, in particular, to deal with these very hard non-trivial problems.
Are there any other questions? Yeah.
So you comment on your training data need to be very precise. How precise do you need for this projection?
Oh, I suspect it will depend on problems, right? But in the nuclear structure, for example, clearly the interpolation, it's actually you have to separate interpolation and extrapolations. So the interpolations normally doesn't amplify your training calculation error. So if you have, say, 10 to the -3 or 10 to the -4 error, the interpolation tend to stay there. But for the extrapolation, you will amplify when you get away from the training region. So if you want to go further away, you need a better accuracy at the trainings.